Hi students, in this video we are going to see the volume of irregular shaped objects and volume of liquids. In finding the volume of irregular shaped objects, we use the water displacement method. For example, I have some water with a volume of V1 and put it in a graduated cylinder, and I put a stone into the water, so the water level will increase to V2 because the object displaces this volume with water. So the difference between the volume of the water in the graduated cylinder will give me the volume of the object. So the volume of stone will be equal to V2 minus V1. In this example, we are going to see how the sand problems are solved. We have a 60 centimeter cube of dry sand. It is added to 50 centimeter cube of water, but the total volume becomes 90 centimeter cube. Always the total volume is smaller than the separate volumes of water and sand because there are air molecules between the sand particles. So when we say we have 60 centimeter cube of dry sand, it is equal to the volume of air plus the volume of only sand particles. So not 60 centimeter cube of dry sand is just sand. So how can I find the volume of air between them? The volume of air is equal to the volume of sand plus the volume of water minus the total volume. So here in A was the volume of water that fills the air spaces between the sand particles is equal to the volume of the air, which is equal to 60 plus 50 minus 90 is 20 centimeter cube. What is the volume of the air space between sand particles is the same, 20 centimeter cube. C was the volume of the sand particles alone without air space. So with sand only is equal to the volume of sand minus the volume of air, which is equal to 60 minus 20, 40 centimeter cube. What is the volume of water that doesn't go into airspace between the sand particles? So it's equal to volume of water 50 minus 20 centimeter cube going into air spaces, so the rest will rise in the cylinder. What percentage of the total volume of dry sand is air space? I have 60 centimeter cube of dry sand. It has 20 centimeter cube of air. So in 100, how much air I have will give me the percentage. So X is equal to 20 times 100 over 60, which is equal to 100 over 3%. In measuring the volume of liquids, we use graduated cylinders, and it's very important to read a graduated cylinder. Always read a graduated cylinder at eye level. Also, water in a graduated cylinder has a curved surface called meniscus. So read the volume at the bottom of the meniscus. This curve is called meniscus. You are not going to read this part. You are going to take your eye level tangent to the meniscus and read this value. Now let's read the given volume of the liquids. Now I'm going to read the bottom of the meniscus, which is equal to 6. In the second one, take the level from the meniscus, which is equal to 37. The third one, when I take the bottom of the meniscus, it is 1 pitch below the given value, which is equal to 32 centimeter cube, I guess so. And the fourth one, the bottom of meniscus, which is equal to 19, and in the fifth one the bottom of meniscus is equal to 39 centimeter cube. In this question we have a container. It is filled with water at constant rate. That means that equal volume of liquid in equal time intervals, and the relation between the height of water and time is asked as a graph. Now, as the segments are equal, then I can say that each segment can be filled in the same time, let's say t. First, the first segment will fill in a time of t, and the height will be equal to, let's say, h. So my time height graph will be, the height will be h in a time interval of t. So draw a graph like this. And after that, this part will be filled, and the time elapsed will be equal to 2t, and the total height will be equal to 2h. So in our graph, 2t time passed, so I come to the time 3t, and the height will be equal to 2h. So it will be a lower rate graph. And then the flowing liquid will flow here, so fill this part. So while filling this part, there will be no rise in each section. So the time elapsed will be t, 3t, but there will be no increase in rise of the height. And then it will begin to fill these bars. So 5 segments means 5 more t, which is equal to 11t, and come to a height of 3h. So I have a graph like this, and then these parts will be filled. So 2t time pass, and the total height will be equal to 4h. So let's put it here. 13t, the height will be equal to 4h. So the graph will be like this. Where a container whose cross section is shown, it is filled with water, again a constant rate. We are going to draw a graph showing the relation between the height of water in the case section with time. Again, first, this part will be filled in t2 time interval, and come the height as 2h. So drawing the time height graph, the time will be 2t, and the height will come to 2h. And then the flowing water will first flow here and fill this part. So after time of 2t, there will be no rise in the section. So the time will be 4t, there's no rise in height. And then these parts will going to fill in a 3t time. So the total time will be equal to 70, and come to a height of 3h. Our graph will be like this, and then the last part will be filled in a t time interval, giving the height 4h, and the container will be fulfilled. Yes, you know that the gases have the property of dispersion. It spreads out the container they are in. For this reason, the volume of a gas is equal to the volume of the container it is in. So you see that we have 3 different gases with different masses, but they're in the same volume balloons, so they have the same volumes because the volume of the containers are the same.